I changed the title slightly to what was announced beforehand. So the good thing is that you can just jump into the problem without any background in this whole graph complex field. So the setup is very simple. You have a graph which is connected. And we are in the situation that the number of edges of the graph is twice the first Betti number, which is for me now twice n. Yesterday, the n was a g, the genus of Riemann surface, but I just used the letter n. And from the graph, we construct a graph Laplacian. Lambda g, and I don't even define it. It's for us now, it's just a symmetric matrix. Which encodes the information of the graph, and the entries are linear in some edge variables. XE. So for every edge, you get a variable, and this is a matrix where these variables are at certain positions. And the program is twofold. There's an easy step and a hard step. The easy step is to calculate the differential omega g to n minus 1, which is the trace of lambda g to the minus 1 d lambda g. This to the power 2n minus 1. So that will be a 2n minus 1 form, because this is a matrix. It has a non-trivial power. And the second step is to actually calculate an integral I g omega 2n minus 1. And this is the integral over the positive corner simplex in projective space. So we consider this as a projective differential form, omega g to n minus 1, because this is some d log lambda g. It has degree 0, so that's a projective form. And we integrate over. If you don't like projective integrals, then you have to set one variable to 1 and integrate all the other variables from 0 to infinity. That's the affine version of it. So step 1 is linear algebra. And step 2 is doing the integral is something that we may hope to know from quantum field theory. So here is where my interest comes from. I developed this theory of graphical functions. I can do many of these integrals. It depends what this omega g 2n minus 1 will be, but there's a hope that we can use the whole knowledge in quantum field theory, how to calculate Feynman periods, and apply it to this integral. So I won't speak about part 2, only talk about part 1, which is the simpler part, but it's still hard enough to be non-trivial. And here, this is a power, and this is only an index here, the 2n minus 1. So to make this more clear, I want to give the example of the wheel. We had the wheels yesterday. So this is the example. We will have the example in the back of our minds for all of the talk. So we will come back to this later. So there's the wheel, which is just a wheel with n spokes. These are the spokes. So this will be this labeling S1, S2, S3, and so on to Sn. So I'm using the variables S for the spokes, and for the rim, I have R1, R2, and this is Rn instead of variables X. because this makes it more clear what is a spoke and what is in the rim. And then we calculate this graph Laplacian of the wheel. And this gives a matrix. It depends on a choice of a cycle basis, or maybe it's a dual graph Laplacian, then it depends on a choice of a vertex. So it's not fully well defined, but there's a canonical, more or less canonical choice how to do this for the wheel. So it has, the rim is on the diagonal, and it has the neighboring spokes as 1 plus S2. 1, maybe 1, and maybe we should move this one over here. And then there is a minus S1, it's a symmetric matrix, and this has a minus S2, and this goes on to Rn plus Sn minus 1 plus Sn. Then there should be here a minus Sn minus 1 minus Sn minus 1. So these are the minus S here, and Sn we have at the far upper corner and at the far lower corner. Sn. So that would be the graph Laplacian of the wheel. And the determinant of the graph Laplacian is always the graph polynomial, or dual, depends on how you define it. And it's a function of the variables R and S. And then we have theorem 1. I don't really know how to state this theorem, because it's a theorem in progress. So it's not a conjecture, because a conjecture means that we are unable to prove it. It's now being proved. Like, so it will be a theorem. It's not written down fully, but we think about the best way to prove it. So I call it a theorem in progress. And this was Brown. And it's 2021, so 2021 is 22 is not over, so it's a theorem in progress. Maybe later we have a full, should have a full theorem. And it says, it calculates this invariant form. This is called the invariant form, this omega g for the wheel, omega for the wheel n, 2n minus 1. This is the sum k equals 1 to n minus 1 half. There's some constant c k n, and then there is a product of all the spokes to the power k minus 1, and in the denominator we have the graph polynomial of the wheel to the power k plus 1, which depends on r and s. And then there is an omega, which is the volume, the projective volume form. It's a top form in the top projective form. We have 2n variables in projective space. We have 2n minus 1 dimensions, and this is the top form. So that's a unique top form. The constants are, write them down here, C, K, N. If you can't read them, they're not so important. It's just some numbers. Just want to give you an impression. L equals 1 to K minus 1 K minus L. It's K minus L. And there's a 2K over K minus L. And there's an L to the power n minus 1. So it's the sum, a finite sum, but it's nothing really fancy. This is theorem 1 in progress, and then there's theorem 2 in progress. Progress is also and that's the integral, and the integral of the wheels n times 2n over n theta of n, where theta is the Riemann theta. Theta of n is the sum. Now I have used the m as a sum variable. The Riemann theta. And I should say this is a special case in the setup of Franz's invariant forms, because in general we could have more edges than twice the homology, but this is sort of the degree 0 case, which is an interesting case in itself, and that's yeah, the other case is not yet studied by us, but a future project.
Oliver?
We proved the theorem 2 because I want to talk about theorem 1.
Oliver, I think n
The
should be
proof comes from the theory of graphical functions. Basically, it's rather Gegenbauer polynomials that you use, which is
Oliver?
yeah,
Oliver?
we have the integral Rs, this projective integral S1 to Sn to the power k minus 1. You can do this integral and 1 plus k omega. This is proportional to the period of the wheel.
Somebody move
2k
the
plus 2 dimensions.
video so we can see the board.
So this index k becomes a dimension. If k equals 1, for example, we have the maybe familiar psi squared denominator would be 4 dimensions. And the wheel is the same wheel as we had before, but there are weights on the edges. The edges, the rim has weight 1, and the spokes have weight 1 over k. I don't explain what this exactly means, but there are different weights on the rim and on the spokes. And then there's a theorem which we need to prove. This theorem. This is not so complicated calculation. So last year that the period, you can calculate the period 2k plus 2 is get a formula which is 2n minus 2 over n minus 1 and 2k minus 1 to get some numerical factors, k minus 1 factorial n minus 1. And then you get a fancy way to write the sum of single thetas, n equals 1 to infinity, and the product L equals 1 to k minus 1, m squared minus L squared to the power m to the 2n minus 3. And if you expand this product, then you see that some powers of m cancel and you get a sum of single thetas. So it's a sum of theta 2n minus 2k minus 1. This is the smallest case, which comes from k minus 1 powers of m squared. And then it goes all the way up, the weight goes all the way up to the theta of 2n minus 3. And if you want, yeah,
there's a comment. Could someone speak up, please, from the Zoom people? Maybe it works now.
Test, 1, 2, 3.
Yeah, now it works.
Hi.
Yeah.
Hi, sorry. I was just, when you wrote the equation for the integral of the canonical form of the wheel,
yes,
that's only for odd n, right? For odd
n.
wheels.
Yeah, odd n. Sorry.
Right.
And odd. It's 0 if n is even. I will see this later. I just forgot to mention it here. All these canonical integrals are 0 for even n. That's on the next slide. Thank you. So if you want to connect this to something maybe familiar, you may set k equals 1 and n equals 3. This is the standard wheel with 3 spokes in 4 dimensions. Then this product is empty, so this is a 1, And this is theta of 3, because there's the power 6 minus 3, m to the 3 is theta of 3, and this gives us 6 as a factor. So n equals 3, k equals 1 would be the 6 theta of 3. And you plug this into this formula here to substitute and use tricky elementary lemmas to prove theorem 2 from theorem 1. So that's everything I want to talk about this integration. And now I want to talk about this linear algebra problem, calculating this trace of the differential form. So that's now the target. How do we calculate this? So what do we know about this canonical form? There's Francis has something in his article about this canonical form. The first thing that you would think that because the inverse has a determinant in the denominator, and the denominator is the graph polynomial, so naively one would expect that this omega g to the 2n minus 1 would be some polynomial in x, and then there's the graph polynomial x to the power 2n minus 1 times omega. This is naive. And Francis Brown showed in his article that we actually have something much stronger. This some other polynomial q of x divided by c of g, psi g of x, the graph polynomial x to the power n plus 1 half. And as Eric said, the q is a polynomial in the variables, and only if n is odd, and 0 if n is even. There's nothing to integrate over for even n. We only have odd n. So what we see is that there's lots of structure which leads to an enormous amount of cancellations. So it's not a good idea to just calculate it on the nose, like take the definition, calculate it term by term, multiply, and then in the end you find that you have huge, tremendous cancellations. That's not a good idea. So we need a better approach, and we actually want to get something which looks a bit similar to the wheel case, where in the wheel we had a sum of very few terms. It's only n minus 1/2 terms. These are only monomials, and there are the highest monomial would be the n plus 1. The highest power in psi would be the n plus 1/2. This is k equals n minus 1/2 here. This gives this. But this q has lots of hidden factors of psi with small coefficients here in this case. And it's better to pull this apart and cancel as much as you can before you do the actual calculation. Because otherwise, for large n, this will have millions of terms than the numerator. And here it's only n minus 1/2. So we aim for something that looks very similar for general graphs like this. And on the way of deriving this, we want to prove theorem 1. So we do this in 3 steps. And we start from the very general and be more specific with each next step. So 3 steps. Step 1 is the most general setup that you could come across more or less is we have n by n, generic n by n matrices. Generic n by n matrices. B and omega of numbers and forms. One forms. So B will be numbers and omega will be one forms. And the B will be Bij and the omega will be omega ij. And these are just general variables. And a lemma by Francis Brown says, also in this article about invariant forms, a lemma, everything is by Francis Brown. It's 2000, I think it's 2001. But it's a very nice proof when it's 0. Which is a bit surprising if you see it for the first time, because there are n squared omegas, different omegas in here. So you would expect that b omega to the n squared plus 1 is always 0, because then you run out of variables. But this happens much sooner. And there's a very nice proof, which I skip. And what we want to calculate is just one step below the trivial case. So what we want to know is what is b omega to the 2n minus 1. We stop one step before. We don't have a trace now, and b and omega are general matrices. Later, b will be the inverse graph Laplacian, and omega will be d of the graph Laplacian. We need a notation. This is maybe a bit annoying, but it can't continue without a notation. On sets, we have multisets. You need multisets. Yeah. In the indices 1 and n, so we can have something like 1, 1, 2, and we and I write x for a multi set, and then I need also the frequency notation of these sets, which counts how many ones do I have, how many twos, and so on, how many n's. So this will be a vector. The vector in n with n components gives the frequencies. This will in general have any number of elements, but the frequency vector has exactly n elements. So I write x equals, I don't know, it's just I made up this brackets for the frequency. If x is 1 to the y1 and to the y1, and so this gives the frequencies of these things. And so far I'm not have an order in these sets. So this multiset will be in the frequency notation. If n equals 2, this will be 2, 1. It's 2 1s and 1 2. And I always have this brackets if I talk about frequencies, and if no brackets, then it's the actual sets. And we want to construct matrices from these indices by subscripts ij. This is the matrix which has the bij, where I is from I and j is from j. And so far there's no particular order. Later we need an order because we talk about determinants, but then I have only this notation, and then it will be all the sets. Okay, I give an example. So I want to stress that there's nothing really complicated. It's all very elementary. We just have these matrices, we multiply them, use the anti-symmetry of the one forms, and then we get a result. So there's no deep mathematics behind this. And sometimes it's good if you have a problem with lots of structure, if you start with as little structure as possible and gradually increase the structure. Otherwise you get lost in the structure that you have. So that was the idea. That was my idea to start with the general matrices D and omega. So I give you an example. B11, 1, 2 is the same as B2 0, 2 1s, 0 2s, and 1 1. And this is the matrix. We have a 2 by 2 matrix B, B. The row entries are the ones here, ones, and the column index are 1 and the 2 here. And we need a permanent. Maybe not everybody is used to permanence. We need a permanent of a matrix. And this is an unsigned determinant. So the permanent of B11, 12 will be B11 times B12. And if you take this, you reproduce the result. So I have this twice, whereas the determinant would be 0 of this matrix. Well, that's the notation we need. And then I write down the next theorem in progress. Progress, it's also Francis Brown. Myself, 2022. Gives the full answer for this expression that I wanted to calculate. I write it down and later I explain the objects that you see in the formula. It's easier to have it this way. This is what we want to calculate, 2n minus 1. This is a matrix. Everything is matrices here. So I have the ij component. This goes from 1 to n. And it has a determinant in B, full matrix. Then there is a sum over some n minus 2, n minus 1 forms nu in the omegas, in the various omega. And you get a numerical factor. And here is something that I define soon. It's a vector, an n vector, a frequency vector. I take the new component plus 1 minus delta ij. This is a Kronecker delta. And then I have the permanent of B. And now I need frequency vectors. So I try to save a little bit space here, I2 nu. It's the same as this. Plus EI minus EJ minus 1. This is one component, and the other one is I nu 1 minus 1. So this will be the I in this example, and this will be the second, the J in the definition. And then we have the differential form U. And the differential form has to be ordered in a certain way, and there's some signs hiding in just summing over nu's. So there's a hidden sign where we have an algorithm how to calculate these nu's, but maybe there's something more explicit. So what are these? This is the simplest to explain. The II does the unit vectors. It's all zeros and has one at the position I, and that's an n vector. And the 1, just 1 everywhere. And the EI, the nu will be EI 1 or 2 is the frequency vector of the row or column indices of the omega in nu. So row is the first index, refers to a 1, column is the second index, refers to the 2. The nu is built up by omegas, and then you count the frequencies. So I give an example. N equals 2, you get nu equals omega 1, 1. This is just an example, 1, 2, 2, 1. And then you, in this case, you have I1 nu is, maybe you have 2, 2 to have something different here. So you count the first indices, there's a 1, another 1, 2 1s, and there's 1, 2. And I nu 2 is, there's a single 1, and there's 2 indices 2. Oh, there's nothing deep going on here. There's a problem with which forms do occur. There is a rule that you should not have anything negative in the frequency vector because this does not really correspond to a matrix. And there's another rule that they should not be block diagonal in some sense because then it factors and these nu's have 0 coefficients. But I don't want to be specific here. So this sorts the step one, more or less, get an explicit example result for this. The proof would be, there's different ways to prove this. One maybe good idea is to use a system of linear equations. So we have b omega like times b omega to the 2n minus 1. This is what we want. This gives linear equations to the left, and you get the same from the to the right with b omega, and this is 0 by the lemma of Francis. And these equations should be enough to determine this object's up to a single calculation for one specific term. It relates all the terms, all the new. And then you pick one specific term, and then you do an explicit calculation. So maybe there's more tricks around, but that would be one idea to prove this. And maybe that's an efficient idea. So this is step one. This is the general case for arbitrary generic matrices with no symmetries. And the next thing we want to do is we turn to symmetric matrices, because in the end, the graph Laplacian is a symmetric matrix, and that sounds more trivial than it actually is, because there's this omega matrix, and we can set the B. We can just we can for the matrix B, we can just assume B is a symmetric matrix and nothing changes. But for the omega, we see that there are different terms which are different for non-symmetric omega, which become the same if omega becomes a symmetric matrix, because omega 1, 2 is the same as omega 2, 1. So whenever you have in a nu an omega 1, 2 and a different nu an omega 2, 1, then you have to add the terms if omega is symmetric. When you have both terms, then it's 0, because you take the square of a one form. So it's a non-trivial step to go to pass to symmetric matrices. Step 2. Metric B transpose and omega. And it's sensible to do both simultaneously. It's not a good idea to only make omega symmetric and leave B non-symmetric. I only do a special case because that's what Francis has proved. Consider only these terms when nu has all diagonal elements. And omega is an n by n matrix, so it has n diagonal entries. The nu is omega 1, 1. They should be all non-zero, omega and n. And then there is n minus 1 extra omegas, because it's in 2n minus 1 form. And these extra omegas, I consider them as edges in a graph. It's not the graph we started with, so that's maybe confusing now. And sometimes it's convenient to employ a graph theoretical notation for these omegas, but nothing to do with the original graph. So we call this omega h1, omega h2, and an edge is for me just a pair of two numbers. So a 1, 2 would be an edge from 1 to 2 in the graph. Yeah, and an example of this is exactly the wheels. Is n, where we set lambda of the wheels. We set Sn equals to 1, so we make it affine, and we take the differential. And if Sn equals to 1 and we calculate the differential of minus 1, this is 0, this goes away. So we are exactly in the situation that we have diagonal elements and off diagonal elements which are next to the diagonal. And because of the anti-symmetry in the diagonal, we can skip all these Sn's because they are later wedged with these Sn's here. And so that makes no difference. You can just scratch them in a differential form. You can for the diagonal elements, you can just take the R's. So we get here the case nu equals, and there's only one thing that you get, dr1 wedge drn wedge ds1 wedge dsn minus 1. Say it again, if you would like to have, originally you have something s1 plus 1 here, but d1 is 0, this goes away, and ds1 wedge s1 is also 0. So you can scratch this s1 and do this with all the r's. Well, that's the general thing that you have. And if you symbolize this with a graph where you have n vertices, 1 to n, then these diagonal elements would be self loops because they connect 1 to 1. You don't have to use this graphical notation, but sometimes it's good to have this in the back of your mind to see what's going on. And the S1 would be a 1, 2. This connects 1 and 2, then 2 and 3. And this is S1, S2. This is R1. This is Rn. This is Sn. This one. And in this special case where we have all these diagonal elements in the differential form, we have the general idea is, if you look at the formula that we have before, then there is a sign coming up between the upper and the lower, between the orientation of the edge from A to J and J to I, which is the inverse. So we have if you have this variable, then it's a negative sign, as you get from this variable and this and this. So you get a lot of negative signs. Graphically, the idea is, if you have an edge in a symmetric omega, this is the difference of the edges. The orientation is in a non-symmetric. We still should have a trivial orientation in the symmetric case because this gives a sign if you flip the orientation, but that's just for bookkeeping. So what we need to do to do this case is we have to anti-symmetrize the permanent. We have a permanent here, but we anti-symmetrize several terms in the determinant in a clever way. And to do this, we need a definition. For a set of n minus 1 edges, SITI I equals 1 to n minus 1 of edges or pairs of indices. We define the function, I call this sigma, depends on B and on the edge set. This is the edge set. Is the sum of k equals 1 to n minus 1 half. And then there's the sum over partitions of the edge set. Edge set is a disjoint union of pairs of sets I disjoint Ji, where they have the same size as Ji. All these partitions, and we get a sign minus 1 to the k, and we get determinants B I1 J1, determinant B I N I K JK. So we had a sum of products of determinants, and this k is already this k that we later want to have here. You can already see this sum coming up here. Well, this is only a function which depends on a generic matrix, symmetric matrix B. You can have this for general, but we only need it for symmetric matrices, and a set of n minus 1 edges. And with this notation, we can anti-symmetrize, give the result for the anti-symmetrized permanent. Well, this permanent is now anti-symmetrized. And this is a theorem by Francis Brown. This is a real theorem. This is no longer in progress. So it's another theorem by Francis. And it says we have this set of edges Si Ti I equals 1 to n minus 1 edges. And to S is the set of the initial points, and T is the set of endpoints. And yeah, B is symmetric. Then we get, now I use a physics notation for anti-symmetrization because it's just so neat to write down. If you anti-symmetrize the permanent ST, so that's like a quantum mechanics notation. You have S and T sets, and you anti-symmetrize always to swap Si and Ti, and you get a minus sign. You have Si Ti minus Ti Si for all Si Ti. This is an anti-symmetrization bracket. There are two cases. This is either this sigma of B and the edges, if n odd, or it's 0 if n is even. If n is even. And this is what Eric commented on. If n is even, you always get 0 for symmetric matrices. The proof is a bit tricky, so skip this here. I prove it by giving an example. We have n equals 2 and a generic n equals 3. Those ones are something non-zero. And we have two edges which are just take generic edges, S1, T1, from S1 to T1, S2, T2. You can specialize them to 1 and 2 and 3 and 4 or whatever. And then we have the permanent of BST. That's the permanent of the matrix, the 2 by 2 matrix, B, 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 B. In the rows of S1, S1, S2, S2. The columns are T1, T1, T2, T2. The calculated determinant, the permanent, this is BS1, T1 times BS2, T2 plus BS1, T2, BS2, T1. And now you symmetrize this, or anti-symmetrize this, ST, which means you replace S1 and T1, you swap S1 and T1 and subtract. But because this is a symmetric matrix, this is minus this term. There's nothing happening here, this is minus. This term goes away by anti-symmetrization with respect to H1. And this one gets a second term, is BS1 T2, BS2 T1 minus B T1 T2 BS2 S1. And now if I anti-symmetrize with respect to the second edge, S2 T2, you see that you only reproduce the term because this gives S1 S2. This is this one by symmetry, and this gives T2, T1, which is this one by symmetry. So this only gives a factor of 2. And you write this as minus 2 times the determinant of BS1, S2, B T1, S2, B S1, T2, B T1, T2, This should give the same terms. This is this, this is this, this is this, and this is this. And then we go back to our original way we write these things. And I should have said the way I define this sigma, which is here. We take ordered sets. So maybe you want to change the notation and take unordered sets. But here we have 2 to the k times k factorial equal terms if we permute the indices of the I and if we swap I and k, I and j. So permute the indices I, this gives the k factorial, and then you can swap I with ji. And this gives 2 to the power k identical terms. This gives the same matrices by symmetry. So we have 2 terms here, and we write this as minus determinant E. Then there's first edge S1, S2, S1, T1, S2, T2 minus determinant B, S2, T2, and S1, T1. So these are the 2 sets. I1 is one edge and J1 is the other edge, so it's a bit of a trivial case. And here is I1 the other edge, and J1 is the edge one. These are the 2 cases, and these are 2 to the 1 times 1 factorial equal terms. Okay, this is the case what we get for this specific matrix. I just want to mention that for the generic terms which are not having all these terms on the diagonal, we construct the result from this specific terms by a transformation. There is some covariance under transformations. So we consider some transformation matrices Tij is the identity plus the elementary matrix Ij, this row and column transformations. So you add a row to another row and a column to another column. And we have the identity that trace Tij B Tij transpose omega. The trivial identity 2n minus 1 is the trace of B Tij transpose omega Tij to the power 2n minus 1. And this means we start with an omega where we know the terms, which is 0 everywhere, but only as non-zero terms only at the where we have all elements on the diagonal are non-zero. So we start with something which we know, and we transform the B's. So vertex I goes to J in the edge set, and here we have vertex I goes to J in all possible ways in the graph of omega. And this gives the result for the new omegas. This is some general idea. And now we have a bunch of corollaries. Corollary 1 for all omega. We get the result as is the sum of terms instead B, the determinant B times this sigma of some edge sets for some edge sets. Because this transformation only transforms the edge sets, the structure is maintained. You can express a generic result in terms of these functions. And this corollary 1, corollary 2 is that for any graph, we should have said when we had this determinant formula that we have to take the trace at some stage, which simplifies a bit. It does not really change the structure. For every graph G, we have that omega G to the 2n minus 1 is a sum of terms of the form that in the G to the minus 1 sigma G to the minus 1 and for some H sets. And there's only very few H sets. There's not a huge number. It's a finite sum, and there's experimentally it's a small number. And then we have a last step, which is a trivial step or a simple step, step 3. This is we use duality. An old lemma by Francis, probably not even fully due to Francis the one before, but you find it in the unpublished notes on Feynman periods 2009. For any matrix A, n by n matrix, we have ordered subsets, index sets, and we need a notation of the same cardinality. And we need the standard notation. We have Aij. This is what we had before. This means that we construct a matrix from the rows in I, in columns in J as before. Aij is A with rows in I and columns in J eliminated.
Francis just wrote in the chat, it's due to Jacobi.
It's due to Jacobi, so yeah. It's just always the simplest thing to attribute everything to Francis Brown because it's always somewhere in his notes. It's only a lemma, so it's not very difficult. So what is the equation? It's a duality equation. It looks a bit like duality. And this is the last step. We have determinant of A to the minus 1 I J is minus 1 to the sum of the I indices plus the sum of the J indices over that A times determinant A J I. So from submatrices, which you construct from I and J, you go to submatrices where you delete A and J, A and I and J, and you reverse the order of I and J. So the very last few corollaries is 5 minutes. Corollary 1. So we plug this into this formula for the sigma, which I erased right now. So we plug this in. You have to remember it. That omega G to the 2n minus 1. No, it's that was corollary 2. So we have that lambda G. That's what we wanted to know for the invariant form of the graph G. Lambda G to the minus 1. That was the B, and this set of edges, which will be summed over. You have to remember this definition. It was a sum over k equals 1 to n minus 1 half. Then a sum of edge partitions, edge I distinct union Ji, Ji where they have equal size, otherwise it makes no sense. And then everything was written in terms of these things. This gives lambda g to the minus 1 gives a graph polynomial in the denominator, a 1 power, and then every factor, there was a product of determinants of these objects. And every of these factors picks up 1 power in the determinant of lambda g, which gives plus k. And then there is some signs which we know, and the product I is 1 to k, determinant lambda g, and now I eliminate I and j, and I should write j and I, but because lambda is symmetric, I turn it around. It's a difference. So now I have the invariant form is built out of these things. So we get corollary 2 that omega g for any graph g to n minus 1 is the sum of k equals 1 to n minus 1/2. Then we get some polynomials k psi g to the k plus 1 or 1 plus k times omega, where this polynomial pk is an explicit. Don't have a closed formula, but they have an algorithm to determine this polynomial pk, an explicit sums over products of determinants of each product is k subdeterminants of the graph Laplacian. And this is actually something that we really can't calculate. There's no inverse of a graph Laplacian anywhere anymore. The inverse is complicated. The graph Laplacian is a sparse matrix. So we delete columns and rows and calculate determinant. It's always easier than calculating the graph polynomial itself. So that works to a very high number of vertices. Everything that's complicated is gone from this formula. And the last thing is the corollary 3, and this is theorem 1 for omega n. And the proof here, which is sort of interesting because there's some combinatorics going on, we see that every product of these k determinants gives either 0 or this S1 Sn to the k minus 1. So we only have combinatorial factors counting how many of these terms we have. There is no cancellation between these determinants anymore in any way. So it's purely combinatorial. So that's the last. That's the last corollary that I have. Then I wanted to mention for the last 30 seconds. What do we want to do? The first thing, this conference came 1 week too early. We want to implement this and calculate this canonical form for many graphs, and then we can see what integrals we can do. But at least calculating the invariant forms should be okay for many graphs. Another question is if this is actually canonical in some way, or if there are different presentations in this form that could exist. I expect that it's canonical in some way, but it's not 100% clear because there's certain edge sets there could be relations between these determinants, and so it's not 100% clear. And the next third question would be how to extend this to the higher degree case where we have more edges than twice the homology of the graph. But that's a completely open problem. Okay, thank you.
So questions or remarks, please. Do you have any guess or idea for another family like the wheels where this could work very well?
I think it works for any graph,
Okay.
which is primitive in the sense that the number of
Yeah,
edges
yeah,
is
yeah.
twice the number of loops. For the wheels, we get a complete formula. For
Yeah,
the
yeah,
other
yeah,
graphs,
yeah.
so far we only have an algorithm where we calculate this. So I'm not sure it's easy to get another family where you have a full answer, like maybe the zigzags or something like that.
Mhm.
That would be the next thing one could try. But as an algorithm, it should work for